Hello everybody. Last lecture we have discussed about the logic gates, just basics. Okay. This part if you remember or recollect. These are the basics we discussed in the logic gate, last lecture. Floating input in TTL is 1, ECL is 0, CMOS undefined. Okay, what is floating input means? Unused or input which is not connected to any voltage, open to air. Okay. Now we'll use it whenever required. We'll use this part. Okay. Now let us start the logic gates topic. Now keep the heading in the logic gates. Basic logic gates. In the logic gates, keep the heading basic logic gates. Basic logic gates. In the basic logic gates, first one, let us start with AND gate. Keep the heading AND gate. AND gate. As we have discussed in the Boolean algebra, you are familiar with the AND operation. Now gate is the logic circuit which will perform this operation. What is AND operation? You know, all the inputs are ones, then only one. When we discuss the logic families topic, I will show you physically with the help of diodes, transistors or MOSFETs how to make the gates. Just for continue. Now in the digital part, okay, you know the AND operation. Now what we discuss is AND gate. What is AND gate? The device which will perform the AND operation. Okay, the circuit which will perform AND operation is given as AND gate. Why it is called gate? It will allow, what is your gate, what your gate is doing at your home, it will allow you or stop you. Same here, it will allow the inputs or stop the inputs. Okay, based on the inputs, it will give the output. Okay, I will show you. Okay, it will pass the input or it will stop the input. Okay, see here. Here, this is the symbol for AND gate. This part, most of you might know it, but just we should discuss from the basics or continuity. We should take this part also. Okay, this is the basic AND gate. But you might not know few conditions here. Okay, the concept of enable input and disable input. Concept of enable input and disable input. Say take a AND gate. What is enable input? What is disable input? I will explain. Say if AND gate is given with one of the input as 0, what happens? 1, what happens? Let us see. If one of the input to the AND gate is 0, you see here one of the input to the AND gate is 0, other input is 0 or 1, it doesn't matter. What is my output? 1. Sorry, what is my output? 0. So other input can be anything. What is my output? 0. We can say here it is not depending on other input. We call this as, disable input. Okay, the output is, what is the meaning of disable means? Disable means not 0. Disable means output is fixed at one point. It is not depending on the second input. Then we can say gate is disabled. Okay. Then what is enable input? If one of the input to the AND gate is 1, you observe, one of the input is 1, other input is 0, what will you getting? 0. Other input is 1, what you are getting? 1. Okay. Is it clear? If one of the input is 0, so one of the input is 1, other input is 0, I am getting 0. Other input is 1, I am getting 1. Then it is called enable input, or you can say here, if other input is something, whatever may be, it may be A, B, anything, 1 into A, what is the answer? A. So here 0 is called disable input of AND gate, 1 is called enable input of AND gate. It is not for all gates. You can understand, it is only for AND gate. Okay, so what is the meaning of disable and enable inputs? Output is not depending on other input, or output is depending on other input. If gate is disabled, output does not depend on other input, output will be fixed at either 0 or 1. If gate is enabled, output depends on other input. If other input is A, you will get, okay, output depends on other input, you will get the output. Okay, so for the AND gate, 1 is the enable input, 0 is the disable input. Okay, so now let us see how to treat unused input in multiple input AND gate. Multiple input AND gate. How to treat unused input in the multiple input AND gate? That is, see here, you have a 3 input AND gate. You have used A and B, but you have not used the other input. Then what to do for the other input? Can I leave it open, or I should connect to 0, or I should connect to 1? The first point is connect to enable input of the gate. What is the enable input? Logic 1. Okay, so connect it to logic 1. How to connect it to logic 1 means connect to power supply VCC through a resistor. We call it as pull up. If you are connecting to supply, pull up. If you connect to ground, we call it as pull down. So if you connect to VCC, okay, VCC is the power supply, like, which represent logic 1. Ground is representing logic 0 for us. Okay, so VCC means we are connecting to some 5 volts or something according to the logic family. So if you connect to some particular logic voltage VCC, it is equal to 1. Okay, now what is the output you will get? A into B into, what is this? 1. What is the answer? AB. So now it is working like a 2 input gate. Based on the other 2 inputs, we will get the output. That is the concept of enable input. You can understand now. Next, second point. Connect to any of the used input. Connect to any of the used input. Take a AND gate. Okay, now connect it to any of the used input like this. Now if you connect it to B, and what is this? B. What is the answer? A, B into B. What is the answer? AB. Right. Third one. Floating. If it is TTL. What is TTL? Just previously we have discussed TTL logic family. In the TTL logic family, what is the floating input? We discussed 1. So A, B. So leave it open. Just open means what? Leave it floating. Now it is equal to 1. What is the answer? AB into 1, which is equal to AB. Floating input is 1. Here we are not connecting 1. We just left open. But in the flow, in the this family, this open input is treated as 1. You can understand. So if you have a multiple input gate, say 5 input, 10 input, any number of input gate, you are not using all the inputs, you are using only few inputs. Then it is called as floating input. If you are not using all inputs, you are using only few inputs, then it is called as a floating input. Okay. So that floating input you can connect to enable input or connect to any of the used input, or you can leave it floating. This is how to treat unused input in the multiple input AND gate. Okay, connect to enable input, connect to any of the used input, or connect to, so leave it floating in the TTL. You may have the doubt, sir, you have 3 options. If examiner asks you which one is the best option, this is the best option. Why it is best also I'll tell you. In the second one, the disadvantage is fan out decreases. Third one, disadvantage is noise margin decreases. What is that? First one is the best among the 3. The disadvantage with the second one is fan out decreases. Third one, noise margin is decreases. You may have the doubt, sir, what is this fan out, what is this noise margin and all. Okay. When we discuss about the logic families, we'll see how to derive fan out, noise margin and all. But here, to understand the concept, I'm giving you what is fan out. Fan out meaning is, say you have a gate. At the output of gate, you are connecting another gates. So at the output of one gate, how many other gates you can connect? That is given by fan out. What is that? At the output of one logic gate, how many other gate? No need to write, please. We'll discuss that fan out, everything clearly in the logic families. Okay. Simple understanding. At the output of one gate, how many other gate inputs you can connect? This is called as fan out capability of the gate. How we calculate this? It depends on how much current this gate can give, how much current each gate requires. Say for example, this is giving 10 amperes, not 10 milliamperes. Each is requiring 1 milli. Then how many gates you can connect? 10. If you connect more than that, it cannot drive properly. Here what I am doing in the second case, I am connecting 2 inputs instead of 1 input to the same line. Then what happens? Here I'll get 1 ampere here, 1 ampere here, means indirectly this gate is working like a 2 gates. So I cannot connect 10 gates here, as I am already giving 2 milliamperes here, 8 milliamperes is left over, or 8 gates only I can connect. Yes or no? This is indirectly like this. Okay, so extra 8 means total previously 10 gates you can connect. Now you can connect only 9 gates, or you can say fan out will be affected by this logic, this condition. Similarly, what is the third one? This very clearly derive it and everything we discuss in the logic families topics. Just for continuity I have given. The next one is floating input. What is floating input? Here if you leave it open, what is the problem? I have given that their noise margin decreases. What is the meaning of noise margin? See here. At the gate input which is open or something, how much noise you can add? Noise means voltage. Some at the gate, it is at logic 0 or 1. Some random noise has come. Okay. So what will be the maximum magnitude of the noise you can add? That is given by noise margin. Noise margin is the maximum amount of noise you can add at the input of a gate. Okay, it should be as high as possible. Which one is affected by this condition? Okay, how we calculate noise margin, what is that? It depends on voltage levels and all, how to calculate and all we discuss in the logic family. Just for continuity understand, the problem with this is noise margin will be affected or decreases. That is, the noise immunity of the system will be affected. So, out of the 3 available, which one is the best one? First one, connect to enable input. It is given in one of the IES paper also. They have given a 4 input NAND gate or some particular gate. They ask two inputs are used, other two inputs to be connected to, which one is the best option? Like that they have given 4 options. Best one is always connected to enable input. Okay, enable need not be 1 every time. I will show you it can be 0 also. Okay, depending on the gate. First copy up to this. Please copy it. Meanwhile, I'll make for OR gate. You can copy it. Okay, after this, add one point. After this one, after this floating input in TTL, after this third option, write down. So out of the three available options, the disadvantage with the second option is noise margin. Sorry, please strike off. The disadvantage with the second option is fan out decreases. And the third option is noise margin decreases. So the first option is the best among the three. Okay, right. Now keep the heading OR gate. Right. You know OR operation. What is OR operation? any one of the input or both the inputs are 1, your output is equal to 1. This is the symbol for OR gate, y equal to a plus b. Now, similar to AND gate, don't write, please listen first. Similar to AND gate, let us find OR gate also, your basic enable disable input concepts. Listen. If, for example, in the OR gate, if one of the input is 1, what happens? You can see, if one of the input is 1, other input can be 0 or 1. Output is not depending on other input. What is the output you are getting? 1. So, other input can be anything. What is my output? Is fixed at 1. We call this as disable input. Output can be 1 or 0, doesn't matter. Disable means not 0. Disable means output is constant irrespective of second input. What is the meaning of disable? Output is constant irrespective of other input. Okay. Similarly here, if one of the input is 0, what happens? If one of the input is 0, other input is 0, I am getting 0. Other input is 1, I am getting 1. So, other input is whatever you have, the same you are getting here. Sorry. If other input is A, you are getting A. Other input 0, 0 plus 0, 0. Other input is 1, 0 plus 1, 1. So, here 0 is the enable input. It is reverse of AND gate. Please understand, enable disable doesn't mean 0 and 1. Disable means output constant irrespective of second input or other input. Enable means output is depending on the remaining inputs. Okay, so 1 is the enable, so 1 is the disable, 0 is the enable input of OR gate, that is reverse of previous AND gate. Now, how to treat unused input in the AND gate we have discussed in the previous lecture. Now, previous part. Now, we'll see how to treat unused input in the OR gate. Whatever we discussed for AND gate, more or less here also same, but see here. What is the first condition we discussed earlier? Connect to, tell me, connect to enable input. Okay, here also connect to enable input. But what is enable input here? What is enable input here? 0. So connect to 0. I assume 0 is nothing but 0 volts or ground. We call it as pull down. Okay, next. Second one is when you connect to ground, we call it as a technical name pull down. Okay, so here logic 0. Then what happens? What is the output? A plus B plus 0, which is nothing but A plus B. In the 3 input, it is working like a 2 input OR gate. Okay, so that is the first case. Second case, connect to any of used inputs, same as previous case. You have A and B, connect to any of the used inputs. This one, you connect like this. Third input, connect to any of the used inputs. Then what is the answer? A plus B plus B. What is B plus B? B. So what is the answer? A plus B. A plus B plus B is B plus B is B. So A plus B is the output. So it is working like a 2 input. Lastly, previously floating if it is a TTL logic family. Now it is floating if it is ECL, emitter coupled logic family. So here OR gate only, but leave it floating. If it is ECL, floating is 0. So A plus B plus 0. What is the answer? A plus B. Here also the conditions are same. The first one is the best, connecting to the enable input. But here enable input is 0. The second one disadvantage is fan out decreases. Third one disadvantage is noise margin decreases. Okay, copy it again. So here I am not repeating that point, that is first one is the best, second one disadvantage, fan out, third one disadvantage, noise margin, like the previous one. Okay, anyway it is same, already it is given here, no need to take that point again. Okay, so that is about your AND gate, OR gate, enable, disable inputs, and concept of unused input, treatment of unused inputs. Okay, now we'll see the next one, that is inverter. Okay, another name for inverter is NOT gate. Okay, see here, you know inversion means 0 becomes 1, 1 becomes 0, y equal to a bar, 0 bar is 1, 1 bar is 0. So here if you take inverter A, what is y? A bar. Okay, this is the symbol for the inverter. Practically, if you want some example of the inverter circuit like this with switches, say I have a bulb here. If switch is on, short circuit, total current flows through short circuit, no current flows to the bulb, and the bulb will be off. So switch is off. When it is off, current starts flowing through resistor and the bulb will be on. This is called inversion action. When switch is on, bulb is off. Switch is off, bulb is on. This is a small example of the inverter. Okay, inversion means whatever we have input, that will be inverted in the output. If your input is 0, output will be 1. If input is 1, output will be 0. Okay, copy up to this first. Okay, now if you connect inverters in a loop, what happens? Let us see. If you connect inverters in a loop, what happens? Let us see. See, I have an inverter, another inverter, another inverter. I have connected 3 inverters in a loop like this. Each inverter is having a propagation delay of, say, I am taking arbitrarily TPD equal to 1 nanosecond. You may have the doubt, what is this propagation delay, sir? Yes, I will explain. When you apply the input in any logic gate, internally your transistors will be changing from on to off condition or off to on, saturation to cutoff or cutoff to saturation. So once you give the input will be having some capacitance to charge, okay, or load the input. Okay, because of all these conditions, it requires some time to get your valid output. That is called as propagation delay of the gate. What is propagation delay of that gate? It is the time required to get valid output after applying the input. Don't write. We'll see all these again in the logic families. That's why I'm not dictating this point. Okay, just understand. It is the time required to get the valid output after applying your input. After giving the input, how much time is required to get the output? That is called as propagation delay. Okay, say for example, each inverter is having a propagation delay of 1 nanosecond. Then you have connected 3 gates like this. What happens? Let us analyze. Assume initially your output is at 0. It can be at 0 or 1. I am assuming it as 0. Now this loop or this wire will go back, and what is the input here? 0. After giving 0 here, it requires how much time to get the valid output? 1 nanosecond. What will be the output I will get? 1. Because 0 inversion is 1. After another 1 nanosecond. So 1 nanosecond plus another 1 nanosecond means how much? 2 nanoseconds. 1 inversion is how much? 0. Now another 1 nanosecond, that is 3 nanoseconds, 0 inversion is how much? 1 will come. Okay. So here initially 0, after 3 nanoseconds, what is my output? 1. Now 1 will go back. After 1 more nanoseconds, 3 plus 1 how much? 4 nanoseconds, it is 0. Another 1 nanosecond, 5 nanoseconds, it is 1. 6 nanoseconds, it is 0. Now you can understand, it will go back, and after another 3 nanoseconds, that is I will get at 9 nanoseconds. What will I get? 1. Next 0 and so on. So you can observe here the output is not constant. It is toggling from 0 to 1 at 3 nanoseconds. After another 3 nanoseconds 0. After another 3 nanoseconds 1. After another 3 nanoseconds it will repeat the same 0 1 0 1 0 1. So if you try to draw this output, initially it is 0. After 3 nanoseconds 1. Next 0 1. Next 0 1. And so on. It is on for 3 nanoseconds, another 3 nanoseconds, and so on. It is nothing but clock generator circuit. Another name for this is ring oscillator. We call it as a ring oscillator, or it is also what another name, square wave generator. Another very important name is astable multi-vibrator. What is this? A stable multi-vibrator. What is a stable multi-vibrator? It has no stable state. Output is continuously toggling between 2 semi-stable states, 0 1 0 1 0 1, like that. So it is having 2 semi-stable states. Okay. So it is not having any stable state. It will be continuously toggling. We call it as a astable multi-vibrator. Here, this is, we can say, time period of the clock. What is the time period of the clock here? 6 nanoseconds. Or what is the time period of the clock? It is equal to, another formula in this case is 2n TPD. Here n is number of inverters in the loop. TPD is, what is the meaning of TPD? Propagation delay of each inverter. Okay. So here, this is the, and these are the names for this circuit. What is the time period generated is 2 times, 2 3 is na, 2 into 3 is 6. So 2 into how many inverters? 3 inverters into propagation delay of each inverter is the time period of the generated clock. You may have the doubt, sir, 3 I have connected, okay. I will see, let us see what happens if you connect 2 inverters. in a loop. Here also take the same example of TPD equal to 1 nanosecond, 1 nanosecond. So initially it is at 0, for example. Okay, I have opened and applied 0 or anywhere. So initially it is at 0, for example. Here 0. After 1 nanosecond, what is my output? 0 inversion 1. 1 inversion again 0. Or your output is at 0 going back, and what is coming back? 0. It will go back and come back as 0, or you can say output is not changing. It is constant or stable at 0. Previously toggling, but here it is at stable of 0. Suppose if initially 1 is present, if I am assuming output is 1, or if I have given input as 1 after removing this wire, then 1 will go back. After 1 nanosecond, 0, 2 nanoseconds, again 0 inversion is 1. So whatever you have, that will be present. It may be 0 or it may be 1. Again it will be stable or constant. It is not changing. So if initially if you have 0 here, my output is stable at 0. If initially my output is at 1, output is stable at 1. Okay. So here output will be stable at either 0 or 1 depending on initial condition, or we call it as bistable multi-vibrator. That one is astable. This one is bistable multi-vibrator. You read about your bistable, astable, monostable multi-vibrator whenever you discuss, whenever you read your analog electronics subject. Okay. So astable is not having any stable state. Bistable is having 2 stable states. We have one more, what we call it as monostable. That will also come in your digital circuit with the help of sequential circuits we discuss later. Okay. Now here, this is the basic circuit which we use for flip-flop in the sequential circuits. I'll explain that whenever we discuss the sequential circuits. Okay, this is the basic block we use in the flip-flops or memory elements. So initially, if your output is 0, your output is constant at 0. If your output is at 1, constant at 1. It is called stable state. Okay. So it will be at either 0 or 1 depending on the initial condition. So 2 stable states, bistable multi-vibrator. So what is the conclusion we can give here? N is equal to odd. It can be 3, 5, 1, 7, 9, any number. N equal to odd, it is astable. If N equal to even, N means number of inverters, okay, is even, then it is bistable. So if you connect odd number of inverters in a loop, it is a stable multivibrator. If you connect even number of inverters in a loop, it is a bistable multivibrator. Copy it. Based on this, let us have two questions on this. Write on the question. Write on the question. In the ring oscillator circuit shown in the figure, in the ring oscillator circuit shown in the figure, in the ring oscillator circuit shown in the figure, if the propagation delay of each inverter is 100 picoseconds. Propagation delay of each inverter is 100 picoseconds. 100 ps. Pico means 10 power 12 minus 12. Propagation delay of each inverter is 100 picoseconds. Then determine the frequency of the generated square wave. The frequency of the generated square wave. Listen. Direct formula. What is our time period of the clock formula? Just now we discussed 2n TPD. 2 into n is how much here? 5 into TPD is how much? 100 into 10 power minus 12, which is 10 power minus 9. Then what is the frequency of the generated clock? 1 by 10 power minus 9, which is 10 power 9, 1 gigahertz. Direct formula. It is n equal to how much here? 5. 5 means odd, definitely ring oscillator circuit. Yes or no? So 1, 2, 3, 4, 5, you can apply this concept. Copy it. Right on the next question. If each inverter is having a finite propagation delay, then the logic circuit is copy the figure and options. Bistable, monostable, astable, schematic trigger. What is this circuit? We don't know. You read it in your analog electronics. It is a square wave generator circuit irrespective of the input waveform. Okay. That is not required for us. Okay. Options they have given. See, each gate is having some propagation delay here. Now you tell me here. N is odd or even? 1, 2, 3. If you take odd, astable, but wrong answer. Here, please understand. Only the inverters in the loop we should consider. For example, if you have initially some 0 here, what will you have here? 1. After some TPD, you will get 0. After another TPD, what will you get? 1. Or you can say 0. This part is stable or not? Because only this is in the loop. This one is just inversion of the output. If this part is constant, my output is constant or not. So we should never consider the inverters outside the loop. Inside the loop, how many? N equal to 2. 2 means even. So bistable. So don't think that N equal to 3. Okay. Because it is number of inverters is 3. Consider only inverters in the loop, not in the outside the loop. Copy it. So when you are copying your solution, instead of copying the figure again, better to mark like this, okay, in a different color. What is the advantage of this? You need not copy the figure again. Or if you mark it with the same color, later when you refer your notes, you will be confused. What is given by examiner question, what you have done solution. So when you make the notes, note it properly with two different colors. It is always suggestible. Okay. Right. That is about your basic logic gates, AND gate, OR gate, and inverter. Okay. The next coming lecture we see the special function gates, universal gates, and the circuits based on that. Okay. We'll continue in the next lecture. Thank you.